The solar market is booming due to new regulations favoring green energy in Europe and America. There are several requirements and trends that only GaN technology can completely fulfill. In this presentation, first, let's review the EPC target applications and success stories. Then, we will provide an overview of the solar market and compare the different topologies. We will explain why GaN devices outperform silicon devices for solar power, where GaN devices perform the best in the applications, and the EPC product offering for each topology. Finally, we will recap the EPC product portfolio and roadmap for solar. The applications we target are three. First, microinverters. We target a particularly high-density microinverter that can be integrated into the solar panel frame to resolve the hurdle of the installation. In this application, 100-volt and 150-volt devices will be required. Second, we target solar optimizers. A solar optimizer is a 4-FET buck-boost topology requiring 80-volt or 100-volt FETs for a single panel and 170-volt or 200-volt FETs for dual panels. Third, we target the battery management or energy storage system. Backup batteries have been added to all new smart homes or commercial solar systems to provide power in a blackout. 200-volt GaN devices can be used in multi-level and multi-phase configurations to convert from 50-volt to about 300-volt. As opposed to solutions using 650-volt FETs, a multi-level solution offers higher density, efficiency, and better thermal performance. These are two examples of success stories where EPC GaN has been used and allowed to shrink the size, improve efficiency, and reduce system costs due to less cooling required. EPC has many at several companies, but these are the only two that we have customer permission to disclose publicly. One success story is a solar optimizer, and one is a microinverter. You can see the M500 solar optimizer from BRC that uses EPC 2218 GaN FETs on the left side. It solves the problem of shading in photovoltaic systems and is plug-and-play and compatible with every inverter brand. The maximum DC input voltage is 60 volt, and the maximum input power is 500 watt. The output power varies from 0 watt to 500 watt, and the rated current is 14 amp DC. BRC selected EPC GaN FETs because they needed to increase density. GaN FETs are very small and allow higher switching frequency and power density. This design measures only 78 millimeter by 158.5 millimeter by 30 millimeter. On the right side, you can see the JT350 microinverter from Solar Native. Solar Native uses EPC GaN devices to solve the challenge of solar power installation with its new microinverter that integrates into the module frame. The JT350 is the smallest inverter in the world with dimensions of 23.9 by 22.3 by 385 millimeters, an AC output power of 350 watt, and a power density of 1.8 kilowatt per liter. This is 5 times the power density of the state-of-the-art silicon MOSFET microinverter solution, the IQ7A microinverter from Enphase. Despite the extreme size reduction, the European efficiencies are quite comparable. This extreme reduction in volume was necessary because Solar Native wants to offer its inverter not only as an external device, but also as a version for module manufacturers, the JT350-I, for integration into the module frame. The JT350 is recommended for modules between 330 and 440 watts. Solar Native achieves the high power density by using EPC GaN devices, which allows a switching frequency of up to 2 megahertz, thus a simultaneous reduction in inductive components and volume. Let's look now at the three different solar power topologies. A string inverter is a centralized system with a single inverter connected to multiple solar panels and power higher than 2,000 watts. This is today the most common topology because it was the state-of-the-art solution at the time. Still, it has many limitations, and we believe it will be replaced by the other two topologies for residential and commercial use. Microinverter topologies instead feature a smaller inverter for every panel or small group of panels. They are plug-and-play devices that convert DC current by a single up to 6 panels to AC and harvest optimum power by MPPT, maximum power tracking. Typical power ranges from around 350 watt for one panel, 500 watt max, to 2,200 watt for 6 panels. Enphase and Home Miles sponsor this topology. An alternative topology that is getting a lot of traction with big sponsors like SolarEdge and Tigo consists of several optimizers, one per panel or one every 2 panels, plus a single inverter. A power optimizer is a DC to DC converter that maximizes the energy harvest from a solar panel's true MPPT. Single or dual panel solutions are available in the market up to 800 watt. Let's look now at the pros and cons of the 3 solar power topologies. A string inverter has a lower initial equipment cost per peak watt, making the topology very compelling for large installations with several panels. However, it has a shorter lifespan, 5 to 12 years, and will need replacement during the lifespan of the solar panels. Finally, performance is poor because the malfunction of one panel affects the output power and the system lacks monitoring capability. Overall, what one will save initially will be compensated by replacement maintenance costs after, and the energy produced by the same panels is up to 25% lower than the other 2 topologies. As for microinverters, the panels are electrically isolated, resulting in a 5% to 25% higher output power, and a panel failure does not affect the system. The lifespan is more prolonged, 20 to 25 years, so microinverters do not need to be replaced during the lifespan of the solar panels. The system is fully scalable, and adding modules to upgrade to a higher power is relatively easy. The system is capable of simplifying remote control and maintenance for safety. Other benefits are simplicity and low amperage wires. One con is that each inverter needs to be installed adjacent to a panel, usually on a roof. This makes them harder to install, remove, and replace. Some manufacturers have addressed these issues with panels that have built-in microinverters. This resolves the most significant limitation of microinverters and is precisely the value that a high-density GaN solution can offer and what Solar Native could achieve thanks to EPC GaN. Optimizers plus single-string inverters offer the same advantages as microinverters, higher output power and efficiency. The malfunctioning of one panel does not affect the system, and the lifespan is 20 to 25 years with lower initial equipment cost, as the inverter is the only one like it for string inverters. A DC to DC is easily integrated into solar panels to simplify installation, and the output voltage is low voltage DC for safety. However, they are less scalable than microinverters as the size of the inverter is fixed. We believe that in the future, optimizers plus single string inverters and panels with built-in microinverters will replace string inverters for residential and commercial applications. The solar market pain points are: 1. Achieve higher power density for integrating the microinverter or the optimizer into the panel. This is a considerable advantage for integrators and installers, or for more power in the same form factor to support more than one panel. Up to 6 in the latest home aisle solution, or panels with higher power. New panel power is increasing from 350 watt to 600 watt. That reduces the equipment cost per watt. Second, the thermal challenge. Higher power density comes with a higher temperature of components. To guarantee a long lifespan, the maximum temperature of the components needs to be kept below 125 degrees Celsius. More and more expensive heat sinks and cooling are required. Third, 25 years of life requirement to avoid replacement during the life of the solar panel. This requires devices with superior reliability at hot temperatures and excellent thermal performance. Traditional silicon MOSFETs can no longer fulfill the requirements. They cannot meet the power density required to integrate the microinverter into the panel, which requires greater than 1 MHz FSW. This is why, despite the huge benefit, only a few manufacturers offer this option. They need costly cooling to support more than one panel. And finally, silicon MOSFETs struggle to guarantee more than a 20-year life at hot temperatures. The public disclosed reliability issue of solar edge optimizers and the overheating problem of N-phase microinverters are examples of silicon MOSFET limitations. There is a solution, and the solution is EPC GaN technology. EPC GaN technology offers superior reliability for 25 years of lifetime. Our devices are more efficient and reduce power losses by greater than 60%. The excellent thermal behavior avoids the need for a heatsink and complex cooling that saves system costs. The minimal switching losses allow higher switching frequency from 100 kHz to more than 1 MHz for density and thin designs for integration into the panel or for higher power in the same form factor. EPC GaN technology has traction with several solar Tier 1 suppliers, and this prolonged silicon MOSFET shortage EPC GaN devices are in stock with short lead times. Let's look at solar panel optimizers. We believe this is the solution for the future of solar power. A solar panel optimizer optimizes the power from each solar panel no matter how the other panels are performing. It allows the system more output power from a solar panel, which means more energy and more efficient solar systems. A typical optimizer requires 100-volt switches for a single panel and 200-volt or 160-volt switches for dual panels. The most common topology choice is a 4-FET buck boost. Typically, for a single panel, Vin varies between 12.5 and 60 volt, and Vout between 30 volt and 60 volt, and the maximum current is 14 amp. A dual panel optimizer requires double the voltage and current up to 20 amp. This is a hard switching topology, and GaN offers the best figure of merit, RDS on times QGD, and lower power losses resulting in the highest efficiency. EPC GaN technology allows higher power in the same form factor to support more than one panel in a series for MPPT to lower system cost per watt, reduces power dissipation of greater than 60%, and increases frequency up to 10 times for more than triple power density and reducing cooling costs. Let's now analyze the microinverters. There are several topologies for microinverters. The most common is the flyback topology and the full bridge topology. The flyback topology is popular due to its low cost. Still, it has a few limitations. Max power is limited to 350 watt, and power density is limited and does not allow integration into a panel. This makes full bridge topology or optimizer string inverters the best candidate for future solar systems. The primary stage requires 150 volt, and the secondary stage requires 650 volt FETs. EPC 150 volt GaN FETs are ideal for optimizing size and efficiency and are priced similar to silicon MOSFETs with the same RDS on. GaN devices can increase power density and integrate into the panel, which is not achievable with silicon MOSFETs. The full bridge topology allows higher efficiency and power than the flyback topology to drive more panels with the same microinverter and lower system cost per watt. GaN offers higher switching frequency and power density to allow integration into a panel that is simply not achievable with silicon MOSFETs. The primary stage requires 100 volt FETs. EPC 100 volt GaN FET is ideal for optimizing size and efficiency. The proposed topology for maximum efficiency and the smaller size is the LLC. The secondary stage in the inverter requires 650 volt FETs. As an alternative, 200 volt and 350 volt FETs in a multi-level topology could be used for higher density and efficiency. For all solutions, GaN offers higher power density, excellent thermal performance for easier cooling to increase power, excellent reliability for a proven lifetime. An additional benefit is that users can take advantage of GaN performance to increase their frequency up to 1 megahertz for the highest density. The last block we are addressing with EPC GaN technology is the backup battery energy storage system. EPC has customers that selected multi-level DC to DC solutions using the EPC 200 volt FETs to convert from about 50 volt DC to 250 to 300 volt DC. This solution is 3 levels and 2 phases and uses EPC 2215 GaN FETs. The customer was surprised by the advantage in thermal and density that they could get compared to a dual-level topology with 650 volt devices. The benefits of multi-level solutions versus solutions using 60 volt FETs are: it uses components with lower voltage ratings and better figures of merit, higher switching frequency for smaller magnetics and density, lower power losses, higher power density, and lower dV to dt and less stress in the components for a longer lifetime. Let's see why GaN devices allow this significant power loss and density improvement. Here, we compare the benchmark 100 volt silicon MOSFET with our latest generation 5 FET in chip scale and QFN packages. GaN transistors offer lower RDS on in 1/3 of the size, plus significantly lower QG, QoSS, QGD, and 0 QRR. Solar power systems must operate efficiently over a wide range of conditions. Example, duty cycles ranging from 1.2% to 98.8%. While in a different application, a good silicon MOSFET can be selected for a narrow range of operation, trading off RDS on and Q The silicon MOSFET cannot be effective in the whole solar operating range. A significant value of GaN devices for solar applications is that GaN devices offer both low RDS on and low Q. Therefore, the same device is optimized for the whole wide range of operations, duty cycle, current, and voltage. The lower RDS on times the QGD reduces losses in hard switching applications like the optimizer. The lower RDS on and QoSS reduces losses in soft switching applications like the microinverters. Lower QG reduces driver losses in both cases in smaller size, plus the ability to operate up to 10 times higher frequency boost power density. Additionally, the thermal resistance to the heatsink is 10 times better to silicon MOSFETs for better heat dissipation through the top and cooler operations. In summary, GaN transistors have much lower R times Q for superior performance in 1/3 of the size. They have also been shown to be more robust than silicon due to high fault tolerance for overvoltage, overcurrent, superior reliability, and very cost effective. The chart on the right side demonstrates EPC's price competitiveness relative to silicon MOSFET 100-volt products with similar RDS on. Finally, unlike silicon MOSFETs, EPC GaN devices are in stock with shorter lead times. The advantage becomes even bigger if we compare the performance of eGaN FETs versus the benchmark silicon MOSFET for the 200-volt rating. RDS on of the GaN device is 33% smaller, QG is 6 times lower, QGD 80% lower, and QRR is 0. Additionally, the eGaN FET is 15 times smaller. Overall, EPC eGaN devices are 15 times smaller, have fewer losses and no reverse recovery, and enable higher switching frequency. Another essential feature is the unprecedented robustness of EPC eGaN devices. With a test-to-fail approach to reliability testing, EPC test devices well beyond the JetX standard to improve robustness generation after generation. The test-to-fail report, Phase 12 and Phase 14 are available on the EPC website. This report details how by employing a test-to-fail methodology, intrinsic failure mechanisms can be identified and used to develop physics-based models to accurately project the safe operating life of a product over a more broad set of operating conditions. This methodology is also employed to consistently produce more robust, higher performance, and lower cost products for power conversion applications. The results of the report prove the excellent reliability of EPC GaN devices for a 25-year lifetime in the solar mission profile. EPC also offers solutions with integrated drivers for fast market time and the highest density. The EPC 23102 monolithic GaN device offers higher performance and a smaller footprint with significantly reduced design effort requirements for fast time to market. The EPC 23102 is a fully integrated power stage with a 100-volt rating, including the half-bridge FETs, driver, level shifter, and synchronous bootstrap charging. It can deliver up to 35 amps of continuous current. The EPC 23101 monolithic GaN device with a 100-volt rating integrates the half-bridge driver, the high-side FET, level shifter, and synchronous bootstrap charging, and it can pair with an external low-side FET like the EPC 2302 to form a 2-chip power stage able to deliver up to 65 amps of continuous current. In summary, EPC GaN devices are required for the highest power density. They offer the highest efficiency and excellent thermal to lower cooling cost. They have superior reliability and robustness for a proven 25 years of lifetime. EPC has market and technology leadership in the 400-volt and below GaN market. EPC offers a differentiated supply chain cost for fast ramp and continuity of supply. And EPC devices are proven for solar power due to traction at top solar companies. In the appendix, you can find a summary of the EPC FETs for solar power, GaN-compatible drivers, and links to web resources, design tools, app notes, and solar product briefs.